This is the presentation for soil contact erosion, otherwise referred to as Scour. During this presentation, we're going to identify the internal erosion process of soil contact erosion, explain the geometric and hydraulic conditions for initiation of soil contact erosion, and assess the likelihood of initiation of soil contact erosion for parallel flow. We'll start with an overview of the internal erosion process, discuss the geometric and hydraulic conditions for initiation, and then go over some more and less likely factors. We'll start with an overview of the soil contact erosion process. Soil contact erosion is the selective erosion of fine particles from the contact with a coarse layer caused by flow through the coarser layer. For flow parallel to the interface, the particles from the fine layer are eroded and transported through the pores of the coarse material as indicated on the left. Flow transverse to the interface is commonly referred to as filter incompatibility. Contact erosion or scour has been used in the literature to describe erosion of core material at the core foundation contact due to seepage flows within a continuous pathway in a rock foundation, but this is really a form of concentrated leak erosion. USACE added the word soil in front of Eichold's term contact erosion to emphasize that this process occurs at the fine coarse soil contact and not the soil rock contact. Focusing on one pore of coarse layer just above the top of the fine layer, surface erosion of fine particles occurs by the parallel flow which develops into the pore. The reverse orientation also has a gravitational pull. The domain for soil contact erosion is defined by a geometric condition in which pores of the coarse layer have to be sufficiently large to allow particles to pass through, and a hydraulic condition in which the flow velocity has to be sufficient to detach the particles and also to transport them. Continuous erosion modifies the interface geometry and gradation. Soil contact erosion may occur between any granular layer, such as a filter, drain, or riprap, and fine soil in contact with that layer, where high velocity flow in the coarse soil parallel to the contact erodes the fine soil. These characteristics usually correspond to the interface between the core and a gravelly foundation. In this figure, a homogeneous embankment dam is shown, with the potential for soil contact erosion at a layered fill due to segregation during construction, and at the interface with a coarse foundation soil. In the bottom figure, a zoned embankment dam is shown, with the potential for soil contact erosion at high reservoir levels above the core, and for erosion into coarse layers in the foundation. Generally, soil contact erosion is considered a contributing mechanism. For example, it can lead to the formation of a roof or a pipe for concentrated leak erosion. Several examples of how soil contact erosion acts as a contributing mechanism are shown on the figures on this slide. In Figure A, soil contact erosion causes a cavity to develop within the embankment fill. When the pressures around the cavity drop, a roof collapse occurs. In Figure B, a cavity created by soil contact erosion does not collapse and can be an initiator for backward erosion piping. In this particular configuration, the backward erosion piping may not ever be observed. In Figure C, soil contact erosion leads to the loss of stability or unraveling of the embankment section. In Figure D, the eroded fine particles clog a permeable layer and increase pore pressures in the embankment, which may result in hydraulic fracture and uplift of the downstream toe. Several cases of leakage associated with the development of a sinkhole or subsidence have been reported in zoned dikes on the River Rhône in France. The dikes are clay silt embankments with gravel layers on the upstream and downstream slopes, often on gravel foundations. Soil contact erosion occurs when high river levels cause high velocities in the gravel foundation, leading to the initiation of soil contact erosion at the clay silt fill and gravel interface. Soil contact erosion may be interrupted if the water level and Darcy velocity are not high enough to sustain continuous erosion, or if they don't remain high enough for periods long enough to sustain continuous erosion. Sinkholes are likely due to the migration of fine soils to replenish the eroded material from intermittent soil contact erosion events. Now, none of these incidents ended in collapse and failure of the dike, and diaphragm walls were installed through the embankments into the gravel foundation to reduce flow velocities in the gravel below the critical values at the clay, silt fill, and gravel interface. Now we'll move on to discuss the geometric condition for initiation of soil contact erosion. The geometric condition is assessed by comparing the D15 of the filter or the coarse material to the D85 of the base or the fine material. If the geometric condition is not met, which requires a ratio of the D15 of the filter to the D85 of the base to be less than or equal to 7.5, then soil contact erosion is unlikely. If the geometric condition is met with the ratio of D15 of the filter to D85 of the base being greater than 7.5, the hydraulic condition for initiation must be assessed. For comparison, the filter design criterion for the no erosion condition for base soils with fines contents greater than 85% is a ratio of D15 to the filter to D85 of the base of less than 9. The geometric criteria for filtration have been extensively researched and are well developed for non-plastic soils. Particle retention criteria can also be used. The no erosion condition and the application of Foster and Fell 2001 for filters that do not satisfy modern filter design criteria to evaluate soil contact erosion of plastic and non-plastic soils are discussed in the continuation presentation. Next, we'll discuss the hydraulic condition for initiation for flow parallel to the interface. When the ratio of the D15 of the filter to D85 of the base is greater than the values in the fifth column of this table, hydraulic loading controls and there is no soil filtration effect as it relates to soil contact erosion. In between these two limits, geometric and hydraulic factors control erosion. This figure shows the influence of the geometric and hydraulic conditions on the critical Froude number for erosion. In the transition zone, the hydraulic loading needed to initiate erosion is higher than in the domain of pure hydraulic influence. Once the ratio of D15 of the filter to D85 of the base becomes greater than about 25 to 30, purely hydraulic conditions control the erosion. The critical Froude number for erosion ranges from 0.65 to 0.7. In this region, the critical Darcy velocity can be estimated using the Bronze methodology from 1985 or the Guido et al. Methodology from 2010, which assumed the lowest value of critical Froude number of 0.65. For a particular base soil, the critical gradient in the coarse layer parallel to the contact where erosion initiates can vary by 1 order of magnitude depending on the permeability of the coarse layer. However, in the same tests, the critical Darcy velocity for initiation of erosion does not significantly depend on the permeability of the coarse layer and is only related to the fine soil's resistance to erosion. Therefore, the Darcy velocity in the coarse layer has been chosen by the majority of researchers as a good indicator of hydraulic loading. Bronze in 1985 measured critical Darcy velocities for gravel above sand. Braun's law is the simplest formula to use, and it gives a good approximation of critical Darcy velocity for gravel above sand. Make a note here that the figure converts the results of the formula from meters per second to centimeters per second for plotting and interpretation purposes. Guido et al. In 2010 measured critical Darcy velocities for gravel above sands, silts, and sand-clay mixtures. Experimental results for the critical Darcy velocity range from 1 to 10 centimeters per second, with the minimum of 1 centimeter per second corresponding to a particle diameter of 0.1 millimeters. This figure was edited from the original by reversing the order of the x-axis and using centimeters per second instead of meters per second for the y-axis. You can note from the figure on the previous slide that the effective particle diameter, or dH, is used on the x-axis of the chart in lieu of the median particle diameter, or D50. This is because during testing, some soils exhibited similar critical velocities but had significantly different median particle diameters, and some soils exhibited different critical velocities despite having similar median particle diameters. In light of these results, it was concluded that the D50 was not a relevant soil characteristic for predicting critical velocity for fine-grained soils. Effective particle diameter, as defined in Kozeny 1953, should be a more representative particle size description for a base soil. This slide shows a simple example of how to calculate effective particle diameter for a given gradation curve. The first four columns are the cumulative particle size curve. The fifth column obtains the fraction within each particle size increment. The sixth column obtains the average particle size for each increment using a logarithmic scale. The seventh column obtains the ratio of the fifth and sixth columns, which is then summed. The effective particle diameter is the reciprocal of that sum. The Guido et al. Equation for critical Darcy velocity for fine soil, including sands, silts, and sand-clay mixtures, is shown on this slide. The equation used the critical Froude number of 0.65 from the bronze methodology instead of a coefficient of 0.7 that's referenced in the Guido et al. Methodology. This is done for conservatism. The Guido et al. Methodology can be used for sands as well as silts and sand-clay mixtures below gravel. The bronze methodology is shown on this figure as a blue line for reference, and it should be used for simplicity for sands below a gravel. The bronze methodology is equivalent to the Guido et al. Methodology within the range of applicability. Experimental data for fine soil above gravel is limited. This phenomenon is complex and it can't be directly linked to river erosion. The influence of confining stress on critical Darcy velocity was noticed, and measured critical Darcy velocities were of similar order of magnitude as gravel above fine soil, i.e. between about 1 and 10 centimeters per second. For silt above gravel, where erosion might be expected to initiate when silt particles fall into the gravel, initiation of erosion is dependent on the transport of particles, not by detachment. So as seen on the previous slide, the hydraulic conditions for soil contact erosion depend on the configuration that's being considered. The hydraulic criteria are reasonably well developed for non-plastic soils, but have significant uncertainty. The hydraulic criteria for plastic soils requires further research, which should account for the similar nature of the erosion process to the mechanics and methods for concentrated leak erosion, but should also give due consideration to the fact that the hydraulics of the flow for soil contact erosion are more complex. We'll briefly show some more and less likely factors that you can consider in your evaluation of soil contact erosion. This table addresses both the geometric and hydraulic conditions for initiation of soil contact erosion. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The bullets indicate to consider the hydraulic condition for initiation when the ratio of D15 of the filter to D85 of the base is greater than 7.5. To wrap up, we'll provide a brief description of the worksheets available in the RMC Soil Contact Erosion Initiation Toolbox. The toolbox contains 3 worksheets to aid in your evaluation of soil contact erosion initiation. The first is a base gradation evaluation that performs a particle size analysis of your base soil and calculates the effective and median particle diameters. The second worksheet is for the bronze 1985 methodology to estimate critical Darcy velocity in a gravel layer for a sand below gravel. And the third worksheet is for the Guido et al. 2010 methodology to estimate critical Darcy velocity in gravel layer for a sand, silt, or sand-clay mixture below gravel. To wrap up, I'll quickly list the references that were used in this presentation. This concludes the presentation on soil contact erosion.